Okay, so thank you. Good morning, good afternoon, good evening to all of you, and hi to the several friends I see connected to this very exciting meeting. So I think that we are ready for this second session of the invited talks for this for the next hour. If Freek is online, then I would ask him to share the screen, and I will give you a warning 2 minutes after your, before the end of your presentation. I will also, sorry, I'm also sending the link of the Slack channel so that you can all go there and possibly continue the discussion and the conversation there. Okay.
Okay, yeah, thank you. So I'll give an overview of the ngEHT analysis challenges that we've been doing for the last few months. I'm coordinating these together with Lindsay Blackburn, and as you can see, we have had help from a lot of people. So what are we doing? We start from a so-called ground truth source model, and this can be tailored to any science case for the ngEHT. So you see on the bottom left an example of an image of M87 where we can see the extended jet in addition to the black hole shadow. And this model can be multi-frequency and static or time variable. And then we simulate ngEHT observations of the source model. And for that, we can use different arrays and design choices. For example, for the number of dishes or their diameter, and then add in realistic observation and calibration effects, so that in the end we get a simulated observation that would be very similar to the data product you would actually get from the ngEHT when observing a model like this. And then we hand off those synthetic data sets to the challenge participants and then ask them to the best of their abilities, try to get all the science out of it that is in there. So what we've been doing so far is just image reconstructions and movie reconstructions. But in principle, participants are free to analyze the data in any way they want. And in the future, we may also design challenges that are tailored to, for example, black hole parameter estimation. And then after some deadline, when we have all the submissions, we evaluate them using quantitative metrics. So why are we doing all this? Well, challenges like these can be used to identify the strengths and weaknesses of our analysis algorithms and also the array architectures. Because the ngEHT data that we get because of the increased number of stations, improved UV coverage, and we have a higher resolution, different frequencies. It's really a different kind of data than we are used to from the EHT, and therefore these algorithms to analyze these also have to be developed further, and also for these different new science cases that are being explored. And it will also inform the design of the array and can help us optimize, for example, for these dish diameters or the locations and the number of antennas. And to do this, all we need really input from the broad ngEHT community. We need the experts on current algorithms and science topics to really maximize what we can get out of those and develop them further. And we also need new and creative ideas from people who are relatively new to Visible AI imaging and analysis. So really everybody should feel free and welcome to participate in these challenges. So far, we've been doing 2 challenges. We did the first one this summer. And if you want to start with that, it is still open and available. And I'll give some more details on how to participate later. And the goal of this first challenge was mainly to set up and test our infrastructure and process of collecting the source models, generating the data, and submissions through a special website that we set up for this, and the evaluation. And to do this, we used relatively simple source models in the sense that they are non-time variable for M87 and ZJ, and also our data corruptions were relatively simple, and I'll get some more details later. And then the second challenge was released just last week, and this is really more science-oriented challenge because we are adding in the source dynamics, and we're interested in seeing how well these source dynamics can be reconstructed by several algorithms. And we also added a bit more realistic systematics to the data so that it's a bit more like a real data set that you would get from the telescopes. And then for challenge 3 and beyond, those will start probably in early 2022. And there we can go to more specific science cases or array design choices. And this is still pretty open. So if you have an idea, or for example, you see a feature in your model that you think could be interesting to test if you could see it with the ngEHT, don't hesitate to contact us and we might design a challenge around this. And also so far we've only used Stokes I data, so we may include polarization here as well. So just an overview of the 2 challenges that we've been doing so far. So here are the source models for the first challenge. We had this Kappa Jet model for M87 that I've shown before, which is prepared by Christian From. And for Sagittarius A star, we had a static Rive model where you can see a very clear black hole shadow, also provided by Christian From. And as you can see, for Sag A, we also applied the interstellar scattering that blurs the image somewhat. Here at 230 gigahertz and at 345 gigahertz, the effect is much smaller. So for the synthetic data, we've been using 2 arrays. The first one is here in blue, is the expected EHT 2022 array. And in red are the 10 sites that are added to that and together form our reference 1 ngEHT array. And this array has been put together by Alex Raymond, who found that this array performs particularly well on several UV coverage metrics. And for the data corruptions, we've kept it relatively simple. We did not add any systematics to the visibility amplitudes, but just thermal noise. And we based that thermal noise on the known parameters for the existing telescopes, and we had some 6-meter dishes for the EHT 2022 array and a bandwidth of 8 gigahertz. And we also added expected noise from the atmosphere based on the median opacities in April, as published by Alex Raymond in his 2021 paper. And we used EHT imaging to generate this data. And there will also be a tutorial session on Thursday where you can learn how to generate this kind of data yourself. So here is just a selection of the submissions we got for M87. On the left, we see reconstructions from using the EHT 2022 array, and on the right with the ngEHT array. And you can see in the UV coverage plot that indeed with the ngEHT we get a much denser UV coverage and also a few longer baselines, so higher resolution and higher fidelity for the images. And we see indeed that all these images improve when we go from the EHT 2022 to the ngEHT. You can see a lot more detail in this low surface brightness region of the M87 Jet. We were a bit surprised to see that already with this EHT 2022 array, we could see some of the extended jet features, for example, in this reconstruction on the top left here. But we'll have to see how this holds up when we are adding a bit more realistic data corruptions to our synthetic data. So that's something to look at in the next challenge. And for the evaluation, we've used relatively simple metrics so far. So here you can see the closure phase and visibility amplitude chi-squared, and the normalized cross-correlation, which is a measure for the similarity between the reconstructed image and the true input source model. And this indeed seems to do a good job in that it does increase for the images where we see an improvement. But in the future, we may explore some different metrics as well. In this M87 case, for example, it could be interesting to look at some dynamic range metrics so that we can really measure how well we can reconstruct these low surface brightness features. And then here are the submissions, or some of the submissions we got for Sagittarius A*, and this was aimed at reconstructing the black hole shadow, which all reconstructions do. And we see a clear improvement when we go from the EHT 2022 at 230 gigahertz to the ngEHT at 345 gigahertz, where in addition to the extra baselines, we get a significant improvement in the resolution here. And there indeed we see that you get very nice sharp images of the black hole shadow. For challenge 2, we are now adding dynamical source models. So for M87, we are using this GRMHD movie that was provided by Razi Imami and Kaushik Chatterjee. And we have 20 frames here separated by 20M, and that corresponds to a weekly observations of M87 for about 5 months. So this would be sort of a long-term campaign for the ngEHT, and we hope that we can get some movie reconstructions from these source models. And we're also adding in 86 gigahertz here, and after me, Sara Issaoun will give a talk about the prospects for 86 gigahertz observations with the ngEHT together with other arrays. For Sagittarius A*, we use 2 different source models. So this is the first one. It's a RIAF model plus a shearing hotspot that was provided by Nghd. And this movie is about 4 hours with a 30-second resolution. So over the course of the full day of observation, this movie is repeated a few times so that we have a few instances of this hotspot shearing and falling in as we are observing, and hopefully we can get some movie reconstructions of this so that we can really track this spot falling in. And we see here that in the scattered images, the scattering is pretty severe at 86 gigahertz, but at the other frequencies, you can still see the black hole shadow quite well. Then in addition to this sort of well-defined variability, we also have a more turbulent model. So this is a GRMHD movie which is about 12 hours and has a resolution of 221 seconds. And here it will be interesting to see how well this turbulent variability can be reconstructed from ngEHT observations.
2 more minutes, Freek.
Okay. So we use this for generating the data, we use the same arrays as for the first challenge, and we are adding a bit more realistic data corruption and calibration effects using the Simba synthetic data generation software. And this will also be covered in the tutorial on Thursday, where we add in a model of the atmosphere and calibrate the synthetic data. We're also adding systematic amplitudes offsets in the form of pointing offsets that are 2 arcseconds for all stations and stable over a scan. And we network calibrate the data before handing it to the participants to solve for some of the gains of the stations with very short baselines. Now, with all these models and frequencies and arrays, we get a lot of data sets, especially for the M87 one, which has been observed for 20 days. So that may seem a bit daunting, but you shouldn't feel obligated if you participate in the challenge to analyze them all. You can really just focus on particular model, for example, that you find most interesting or that you think you have a good algorithm for. So we've released this challenge last week, and you can find all the information and instructions on our analysis challenge website, which is challenge.ngEHT.org/challenge2 for the second challenge. If you download the data there, you will be asked for a password, and you can get that by asking on the Analysis Challenge 1 Slack channel, or if you don't have access to that, you can also send an email to Greg Lindahl, who has set up the website and is maintaining the submissions at this email address. And our submission deadline for this challenge is 3 December. So you have about a month to look into this data. And also we plan to release an example imaging script that can be used as a starting point for analyzing the data for those who are relatively new to VLBI images. And if you want to have a more detailed look at the Challenge 1 results, there's a write-up of those results available as well in the challenge downloads. And as I mentioned, you can still download the data and submit for Challenge 1 if you want to start with those data sets, which should be a little bit easier than the second challenge. So I'll leave it at that, and we are looking very much forward to your submissions. Thanks.
Thank you very much, Freek. I think we have time for one question. Okay.
So if there are no questions, Freek, this is great stuff, and of course it echoes the wonderful imaging challenge we had with the EHT, which was really so successful and so needed. So are you and Nghd contemplating prizes? I mean, we need to incentivize people somehow. So what do people get if they have the best image?
Yeah, it's a good idea. We haven't thought about that yet, but could be a nice incentive for people to really get the most out of these data.
I would suggest a large cash prize of some kind, but that's just my suggestion. Really good stuff. Thanks.
Shep, if only he could talk to the director of the ngEHT about that.
Yeah, really. I'll put a good word in. Let's chat about that. I think we should have some prizes.
Okay, thank you, Shep. Thank you, Freek. I suggest that you stop sharing your presentation. Thank you. And Sara?
Yes.
Can share hers. Okay, thank you, Sara.
Can you see my screen okay?
Yes, yes.
Okay, great. Thank you very much. So I'll talk a little bit about this apparently well-advertised talk. And it's great to hear that there's interest in the 86 gigahertz capabilities with the ngEHT. We started this kind of mini concept study a couple of months ago. I'm co-leading this with Don Pesci and Freek Roelofs, and a number of people have contributed to the content of our work and these slides. For the sake of nomenclature, I'd like to just mention that we've made a couple of wording changes. So what we call ngEHT in this talk are the new sites to the next generation EHT expansion sites, the upcoming sites. And then when we mention EHT, we obviously mean the EHT core sites that are currently operational with the EHT. So key questions to explore about 86 gigahertz, we kind of split this study into 3 questions. The first one is, of course, how do 86 gigahertz observations enhance the science capabilities at 230 and 345 gigahertz? This is basically, observing together with the other 2 higher frequencies, either in pairs or simultaneously with 3 frequencies. Then what are the capabilities of just standalone ngEHT observations at 86 gigahertz, either this expansion array on its own, or with existing or upcoming facilities like the Global Millimeter VLBI Array or the NGVLA. And then the third one is, of course, because 86 gigahertz would open up a significant fraction of observing time at these sites when 230 and 345 is not possible, how can ngEHT actually be utilized as a community instrument for loads of science that could be achievable at 86 gigahertz, but not essentially related to the ngEHT science goals? So of course, the first big chunk of why 86 gigahertz is great for ngEHT is, of course, multi-frequency imaging. So there's a really nice demo done by Andrew Cheo of imaging at 86 gigahertz and at 230 gigahertz with the current arrays, and whether individually you would get the jet at 86 gigahertz, but not the shadow, and vice versa at 230. And by combining multi-frequency and super resolution at 230, you could then recover the shadow at 86 and recover the jet at 230. So connecting the black hole shadow to the jet and outflow physics is a key component of what we'd like to do with ngEHT, and 86 gigahertz could significantly enhance that because we're looking at an optically thicker regime. And also, multi-frequency imaging would enable spectral index studies across 3 frequencies instead of just 2 near horizon ones. And also, because of the huge increase in sensitivity for the ngEHT recording bandwidth compared to current GMVA, we could also even do polarization maps for our low polarization sources, especially for Sagittarius star, and do rotation measure maps as well. Additional science goals that will be beneficial for ngEHT would be for Sagittarius star, things that require quasi or simultaneous observing at 86 gigahertz, like time lags, core shifts, and flaring behaviors, understanding flaring mechanisms and possible jet evidence in Sagittarius star. Flaring behavior in particular, 86 gigahertz, the radio emission region falls within the orbit radius of these infrared flares that have been observed by gravity. So we'd be observing that simultaneously if we had 86 gigahertz. Then this was also mentioned in Maria's talk and also yesterday, that phase referencing in astrometry would be greatly beneficial. And the advantage that 86 gigahertz gives is really that it anchors ngEHT and the EHT core sites to a well-exercised astrometric network of these lower frequency instruments that are currently operating. And these ones, obviously, we know their positions with great accuracy. This would be really beneficial to anchor the ngEHT to this network. Then there are secondary benefits like telescope calibration. So if you know receiver alignment, you could point and focus at lower frequency at 86 when weather is marginal at 230 gigahertz. This opens up also observing time at 230 gigahertz that would not be otherwise achievable. And also, because we can observe at 86 gigahertz for much longer and for a lot more time of the observing year, we can have long-term monitoring of our near horizon and jet sources as well. Then how does 86 gigahertz as a standalone capability compare with current and upcoming 86 gigahertz arrays? So here we did 2 comparisons, one with the current global millimeter VLBI array, which operates at a bandwidth of 4 gigabits per second that is currently limited by the bandwidth of the VLBA and other NRO facilities. But then the future big NRO projects, of course, the NGVLA, which has really high bandwidth, but because it is a lower frequency array, its coverage is limited. So the great advantage that ngEHT has is that it has the best of both worlds. It has the long baseline coverage that is needed, and also the higher bandwidth recording capability. So here are 2 ngEHT basic array designs, A and B. The difference between A and B is just the dish size and some small differences in sites. They're mostly about the same. So I'll just rapidly flip between the 2, and you can see that for the GMVA, the difference is minimal in the east-west, but it is significant in the north-south. You can see the improvement. And for NGVLA, the improvement, of course, of ngEHT is quite significant by a factor of 2 increasing resolution in the east-west, in the north-south direction, and about half in the east-west with ngEHT. So observing with ngEHT and the EHT core would already give an 86 gigahertz array that is significantly more capable than the upcoming facilities on their own for high resolution imaging and high bandwidth. Here we also show fractional changes in UV coverage over the course of a year. This is relative to the yearly median value for the 3 frequencies at which these ngEHT sites will be observing. And we wanted to show the stability of 86 gigahertz and the stability of the capabilities for the entire year. And you can see here for the summer months, of course, we see dips in filling fraction on this coverage because of high humidity in the summer for the northern sites, which are a majority in the array. So for all of the sites, they're actually much more stable at 86 gigahertz, which you can see here. Actually, the shaded regions here are differences in weather, and at 86, it is really, really minimal. So 86 gigahertz observing could actually fill out telescope time when the weather is too poor for higher frequency observations, which actually gives us a very high utilization of the array, even when it's not observing at 2:30 and 3:45. And because of this high utilization of telescope time, this also enables more flexibility for an interface with other facilities, such as the GMVA or the ngVLA. And this flexibility opens up, obviously, science that is beyond near horizon ngEHT goals like maser studies and even transient radio source triggers that could be facilitated with 86 gigahertz. We also looked at these other weather conditions, whether there would be site dropouts, whether coverage was guaranteed if there was any site that would actually drop out for most of the time because of high opacity. So we set a dropout range of about 0.5 in zenith opacity. And actually this never occurs during the year at 86 gigahertz. So it is guaranteed all full coverage of all sites at any time of the year compared to their higher frequencies. Another thing we wanted to highlight is the combination with the ngVLA. So this is work done by an undergrad, Romy Aran, together with Dom and Freek. And he looked at how the ngVLA imaging would get enhanced if we added the ngEHT sites to it. And here ngVLA obviously has high image sensitivity, but ngEHT sites would give the resolution needed to boost it. So here's a simulation of the M87 Jet at 86 gigahertz. This is what the ngVLA would see. So mostly, the inner jet and probably more of the outer jet at 86 gigahertz. If you add the ngEHT, you could actually see more finer jet features, and also you see a flux depression in the center. And actually, we could spatially resolve a central brightness depression if the 86 gigahertz emission near M87 is sufficiently optically thin. And this is quite incredible because with the ability of ngVLA to observe a lot at 86 gigahertz and ngEHT being available for 86 gigahertz observing, we could actually make M87 movies of the shadow and the jet at 86 gigahertz for a very long time, which would be pretty amazing to study the jet and shadow connection. Then as a community instrument, what you can do with the ngEHT, so the entire observing year is available for 86 gigahertz science whenever 2:30, 3:45 conditions are poor. We looked here at the resolution and the point source sensitivity. So point source sensitivity is coverage dominated, and resolution is obviously the longest baseline spacing. And we looked at the different array combinations and current and future 86 gigahertz arrays. And here ngEHT obviously has excellent angular resolution. So here we mean these expansion sites without the EHT core, but relatively poor sensitivity. If you add the EHT core, you get the sensitivity and the resolution required, of course. But for most of the year, if the EHT core obviously has, the telescopes are doing their own science programs, the ngEHT sites are still available to give the resolution boost. And the ngVLA here has excellent sensitivity, but relatively poor angular resolution. And if you combine the two, which is possible for a large fraction of the year, you get the best of both worlds. Basically, you get the high angular resolution and the high image sensitivity.
2 more minutes, Sarah.
Yeah, great. I'm at my summary. So just to conclude everything that we've said in the talk, 86 gigahertz would boost higher frequency science and observing capabilities with multi-frequency imaging, with phase referencing, and variability studies and calibration. It is guaranteed coverage and sensitivity the entire year at 86 gigahertz from the ngEHT sites. And in combination with current and future arrays like GMVA and ngVLA, we offer both high sensitivity and resolution. And now the next big question is the combination with the receiver study. What is the cost efficiency of, do we need simultaneous 86 gigahertz with the other 2 frequencies versus either having it as a separate band for frequency switching or, dual band, either having it in pairs just with 230. So if you have more ideas for 86 gigahertz utilization, both related and unrelated to the ngEHT science goals, please get in touch with either me, Dom, or Freek, or anybody from the team and get involved with this project. I'll end here. Thank you.
Thank you very much, Sarah. It's a very interesting opportunity and possibility. Are there questions for Sarah? Okay, Marshall, go ahead.
Well, actually, I thought Raze had his hand up first. So my view here.
Oh, okay. I'm fine either way. Sir, that was very fantastic, actually. I got 2 related questions. One is that practically, how hard would it be to add a receiver of 86 gigahertz? And the reason that I'm asking this is that, that actually brings me to the second question, that how much you may actually extra get if this is not super hard to add it to the ngEHT when you go further down to 43 gigahertz.
Yeah, that's a great question. And I think, so there is a separate receiver study also done together with this 86 gigahertz kind of science study stuff. If Gopal is still on the call, maybe he'd like to comment. As far as I know, the tri-band receiver is hard to do. And currently the design for the ngEHT is just a dual band. So I think there is a significant amount of thought that needs to be put into whether the challenge is to make it tri-band or quadri-band, because to get 43 is actually even better for astrometry and phase referencing. Yeah, for jets. Yeah,
exactly. So, the reason that I'm asking this is that if your purpose is just considering the extension of the jet, why not just directly go to lower frequency? If that's very challenging to add the 3-pair or higher ones, why not just skipping 86 and just go to more extended ones? Well, yeah.
Yeah, I think the issue with even lower frequency is that at 43, it's true that M87 is very interesting, but Side Star is not. So there is kind of a weighing to be done for,
I see.
which is both interesting. Yeah, scattering is very tough at 43. 86 is basically the limit for Side Star.
Sarah,
Okay.
I'm happy to comment on Razi's questions.
Yeah.
So indeed, I think adding 86 gigahertz does complicate the dual frequency receiver design. Anytime you add one more receiver module in a cryostat, it does make things harder, especially if you're going to line the beams together in a single cryostat. The question of adding a 43 gigahertz band, it's actually a lot more complicated when you add that, when you to couple optics into a telescope with such a low frequency, and you also want to admit the 345 gigahertz frequency, it makes the telescope design and the optics very much more complicated. So I think given the science benefits were from Sarah's description was somewhat minimal, I think we should restrict our scope to adding an 86 gigahertz band to the 230, 345 combination. But I think it's still, it's a doable thing, the 3-band receiver, and this is something the receiver working group is going to actively consider and wrestle with that problem. Thank you.
Okay, thank you. I think that we should actually move on. I see many raised hands. I suggest that this conversation and discussion continues on the Slack channel. And I ask Sean to start his presentation. Thank you.
Can you all see that? Well, let me try actually in presenter mode. Is that okay?
Yes, it's okay. Thank you.
Thanks, Tiziana. Okay. I have to say, firstly, thank you for the invitation to participate today. I apologize that I'm not able to participate more fully. It's a very busy time of the year here at ALMA with board meetings and associated side meetings. And of course, living in the virtual world as we do, that adds more complications to ensuring everybody gets an opportunity to meet with the various groups involved. So I'm really sorry I haven't been able to participate more. Of course, I must say that ALMA is very proud of its participation in the EHT and the success that the EHT has enjoyed with its imaging of M80, the black hole shadow in M87. And certainly we are looking forward to the next generation EHT and the role that ALMA may play in that and a vital role we anticipate in the ngEHT. And certainly Shep and I have had some conversations along that line and very much looking forward to what the ngEHT actually comes to be. I'm going to describe today this very bright future that we have for ALMA that's been put together as part of a road mapping exercise over the past few years. It's of great relevance to the next generation Event Horizon Telescope, just because of some of the developments that we're discussing, improving sensitivity, changing the correlator, increased bandwidth. And I think there's a number of great synergies that the new system will bring, and certainly new capabilities that it will bring to the ngEHT. And so I'm going to basically provide you an outline of the things that are probably of most relevance to the ngEHT, and delighted to try and answer questions. So what was the path that led us to where we are today? It started back in 2013 with the ALMA Science Advisory Committee, basically thinking about the future of ALMA and how to sort of make best use of or provide some directions for the way that the ALMA development monies were being spent. And they came up with a set of ideas. The board took those ideas and put together a working group to study the science opportunities of what developments, what were the science directions we really wanted to aim for. And so it became a science-motivated development vision. And they were looking to get to 2030, maybe to beyond 2034, even when the ALMA agreement needs to be renewed. That led ultimately to a roadmap being produced in 2018. And following that roadmap, we've sort of discussed what the roadmap implies for the development programs over the course of the next few years and where we should best direct the efforts. And certainly there's been a lot of work in the last couple of years in trying to direct that through a series of workshops on different subsystems where development where we think development should be directed. And really all this development is aiming at three principal science goals as outlined here in the slide. really looking to the origins of galaxies, the first galaxies back at redshifts of order 10, 12, possibly 15, through the peak of star formation to the present day, with some very challenging detection rates. Same with also the origins of chemical complexity, basically tracing the origins of molecules from the beginning of the universe through to the present day, and also looking to better understand the origins of planets and planet formation, particularly motivated by the successes ALMA has had with its observations of protoplanetary disk systems, which has now become a big part of our science, our fundamental science contributions, and with a view to trying to get more resolution to actually study these systems in higher detail. And all these things lead us to two particular areas of where we need to improve our technical capability. We need to improve our line sensitivity. Typically we do that by increasing the number of the amount of collecting area. ALMA's already got quite a lot of collecting area, so we're looking to do that through as best we can through improving receiver sensitivity, and also increasing the bandwidth to try and improve our capabilities when it comes to surveying, which, given the small fields of view that ALMA has, survey speed is a very important aspect of our science operations. So with those in mind, and I should remind you that the ALMA roadmap actually contained a number of things. It asked for essentially at least a minimum doubling of bandwidth, also ideas related to focal plane arrays to improve survey capability, large single dish, and also considering longer baselines. And over the course of the past 2 years, a lot of effort has gone into thinking about those things. And the focus has really come down to basically increasing the bandwidth and improving the sensitivity at the same time. And so that's where the focus is today, is to broaden the receiver intermediate frequency bandwidth by at least a factor of 2, with a stretch goal of 4, and also combined with improved receiver performance. We need to provide a correlator that's going to be able to handle that increased bandwidth, and also give that correlator some capabilities that will allow us to make better use of the spectral reach that we will then have, and ensure that we retain high spectral resolution. Of course, we need to then combine the correlator and the receiver systems in a sensible way, and provide, and then also with this increased bandwidth, you're all very familiar with the challenge of data rates. We have to be able to handle the output from that correlator. So that means we do have to look at the throughput issues. We've got to look at the archiving systems. We have to look at the impacts on data processing and our ability to turn the output of the correlator into science data products. A non-trivial problem when you start talking about a minimum of 2 times the bandwidth with a stretch goal of 4 times the current bandwidth, which is already large to begin with today. This work has sort of been pursued by a number of working groups, the front end and digitizer working group. They actually started their work early on in this process. Their report was finished fairly early. The correlator working group, there was a very successful workshop in Charlottesville just prior to the pandemic. That led to their report coming out sometime in mid to late 2020. We've recently had the signal chain working group report, where they basically considered the front end through the back end through the correlator system, and provided us with some recommendations there. And coming soon is we have to take a look at all the other issues that form the whole system, things like power requirements, how we're going to cool or provide the necessary cooling in the receiver cabins, etc. And of course, in here we also have to consider the software requirements, which are non-trivial for a system for this type of upgrade, and so require some serious consideration. So what do we have in mind for the front-end systems? Well, certainly the doubling of the bandwidth means 16 gigahertz of bandwidth in both polarizations. The stretch goal is 4 times that, 32 gigahertz per polarization. So that at least doubles the spectral reach of the whole system, and therefore gives us the opportunity to increase our survey speed. And depending on the spectral resolutions that you're considering, I'm thinking back to things like this, the pill survey, we could do those factor of 10 or so faster than we can do them today. And also with the increased bandwidth, we get this dramatic route to improvement in continuum sensitivity. At the higher frequencies, we're looking at moving away from double sideband systems to dual single sideband systems, basically to improve sideband rejection, improve our sideband rejection capability. When thinking back to when ALMA was put underway, the capability, this wasn't possible at these frequencies. Today, it's now possible with the devices that exist. And so this is something we're looking at doing. And what does this mean for observing? Well, it certainly improves our observing ability, depending on the configurations that or modes, if you like, that people are interested in. We could be improving our observing speeds by factors of 2, or even, as I said, factors of 10, depending on the kinds of spectral resolutions one is interested in. Just to give you an idea of sort of the ambition, here's a table of receiver temperature goals of the upgrade compared to the current system. You can see there's the band number in the left-hand column. There's the performance in the next 2 columns that we have today. And here's the target performance for the new system. And you can see in many instances, we're looking at factors of 2 improvements in sensitivity over current systems. So this is a very ambitious target in many instances. It's going to require quite a bit of R&D work to actually achieve these things, but we're very optimistic that we can achieve these new ambitious goals using today's technologies. I think of relevance to the ngEHT is the next generation correlator that's being proposed right now. I think this is a very exciting prospect for VLBI. We're looking at basically, it has to handle at least the 2 times the bandwidth spec. And it will be, the current design being considered is expandable after the fact by just adding some more hardware, assumably when funding becomes available. And this correlator will be able to handle up to 70 antenna inputs. But I think perhaps it most interesting for the folks on this call is the VLBI flexible capabilities that some of which will be available from the get-go, and other ones that will require some additional effort and resources to bring to full fruition. And just to give you an idea of the kinds of capabilities, here's a list of features that will be available to VLBI. Full 16 gigahertz two polarization VLBI beamforming across any of or all of the 70 antennas at a very high end-to-end efficiency, including not just the correlator, but also the digitizers. That comes at the same time as 16 gigahertz full polarization, high resolution, 218 kilohertz channel bandwidth imaging visibilities, at a slightly lower end-to-end efficiency. It'll have true delay beamforming. So there's no limit on the beamforming aperture or the number of antennas involved in forming those beams. There's going to be VDIFs figured outputs of up to 224 megahertz bandwidth, of which the central 200 megahertz will be science quality. You'll be able to reduce that to whatever capability the recorders may have to, if you feel that you can better manage this as a different bandwidth. There'll be 4 tunable filters, decimators, for giving you the opportunity to do higher resolution spectral line work, for example. There will be up to 16 VLBI subarrays possible, with different delay centers, each of which can be independently tuned, subject to the various LO resources available. Thinking about that, here's an example of what you might be able to do. Split the array, the antenna resources into 2 different subarrays. Look at one frequency with one array and look at a different frequency with another array. You get the reduced sensitivity of splitting the collecting area, but you're able to do effectively simultaneous frequency observing. And then another thing is there'll always be a VLBA, the capability to have a VLBI antenna output from a predefined, up to 4 predefined antennas, always available, independent of what else the correlator may be doing for imaging visibilities. So this is a truly flexible machine. And certainly, I think a lot of these features are going to be, I imagine you guys are going to be licking your lips with the opportunities this presents. So these are not the only things that are going on right now. There are other things that are relevant to this development pathway. Band 1, the low frequency band of ALMA, we are in the process of receiving those receiver systems from Asia A at the moment, and incorporating them into the telescope currently. Band 2, that design work is ongoing, and it comes wideband ready. It already is increased the bandwidth over what was originally specified for Band 2 and pushes quite a way into what was traditional Band 3 terrain. We have Band 6, our most popular band by quite some way. I think Band 6 is involved in over 50% of the ALMA publications, so a very important band. We have a proposal for a 2.5-year prototype development that's right in front of the board right now. The AMT have recommended that for approval, and the board is going to consider that and give a verdict next week. Very exciting and a prospect, and I think really points to the bright future that widebanding the array will provide. And we also are working on the hardware in the loop simulation environment that will be a very important part of providing support to the wideband system upgrade, largely because it means that we have this environment where we can do an awful lot of testing without actually taking the array out of everyday science operations completely. So that's an important development tool that we're trying to complete. There are other things ongoing right now. The ACA spectrometer is being installed. We have the next generation observing tool in development right now, and also relevant to the ngEHT and other VLBI possibilities. We have APP2 that's currently being worked on, and there are other things that are ongoing, but not quite of the scale of these other projects. And of course, there are going to be new ideas come along. Heaven forbid that they don't. And we're going to have to balance those against the needs of the wideband system upgrade. The challenges that we face and opportunities we face. So certainly, COVID was not a welcome interlude in our lives for any of us, I'm certain. And certainly that really impacted the development program at ALMA quite a bit. We basically the observatory was shut, and so we weren't receiving any new, certainly like band 1, those shipments stopped. Back in the regions, laboratory processes halted. But having said that, quite a bit of research and development effort still proceeded, certainly on the research front. And so I think we were very fortunate that even though we may have been working from home, it was possible to continue quite a bit of the R&D effort with that situation that many of us were in. I think one of the things that the wideband system upgrade brings is that this is quite a large scale development. It impacts almost every subsystem in the telescope. And so it requires an awful lot more collaboration across the project than we have had in our development programs to date. There's a lot more requirements that impact efforts going on in the various partner regions. And I think the other thing is we've now been operating the telescope for a decade. And so there's quite a lot of operational insight that can be brought to bear in the development stage of many of these upgrade projects that can have certainly have cost impacts, for example, in terms of ongoing operations. So what are the timelines? This is all a very ambitious program. Band 2, that's ongoing today. As I said, Band 1, which is missing on this slide, is in delivery. Band 6 is before the board to be considered next week. We have a system requirements review, which is a bit backwards to sort of the traditional way of doing it, but that was a decision that was set in place 5-6 years ago. We do need to do the system requirements review. That's planned for early 2022. We're hopeful that a correlated digitizer proposal or separately will come forward to the board in April next year with an anticipated delivery timescale around 2026. We do have the back end and DTS proposal that does need to come forward, because the plan is to put the correlator at the OSF at 3,000 meters. So we're going to require a DTS system to get the data from 5,000 meters down to 3,000 meters. And then the front end upgrades, starting with band 6, likely to continue through the early part of the next decade, following the priorities as set out in the roadmap. And so that's basically the outline of where we're going. And really all I wanted to say. I'm happy to field questions as best I can. I'm grateful to see that Crystal Brogan, the project scientist for the correlator project, is on the call. So if I can't answer those questions, I'm hopeful Crystal will be able to bail me out. So.
Okay. Thank you very much, Sean. I said there was a question on the chat before Marshall and Shep raised their hands from Michael Jansen. You mentioned the software upgrade to match the ALMA hardware upgrades. Will this be based on ngCasa?
Oh, that's a question I don't know the specific answer to, but certainly I will point out that given the bandwidth increases, we are going to have to definitely look at processing software, and that's going to have to, it'll be interesting to see which one paces the other one, but certainly CASA will need to change for us to be able to make full use of the hardware hardware capabilities of the telescope. Crystal might be in a better position to answer that specifics of that question than I am.
Okay, thank you. Marshall?
Yeah, I was just wondering, and maybe this is too technical to ask for this talk, but I seem to remember you mentioned in there that you were choosing to use 2 single sidebands rather than a dual upper lower sideband. Can you say anything about why you made that decision?
I think just because the capability of the sign by noise, the noise rejection is much improved. But I'm certainly not the expert on that, Marshall. And I think those decisions, it's largely motivated, I think, by development work in NEOJ, which is proceeding at pace, that show that using a dual single sideband system is now feasible.
So this is Crystal Bergen. Maybe I can answer with a little bit more context. Basically, if what you want is continuum sensitivity, then you can get that by making a really wide bandwidth, which people are working on. And sometimes it's best to do that with double sideband, because even though you're taking a big noise penalty, if you can make the bandwidth wide enough, you can get that sensitivity back if you're interested in continuum science. However, ALMA is extremely interested also in spectral line science, and there is simply no way to make a double sideband receiver that preserves really high spectral sensitivity. In other words, when you can't win from the bandwidth, double sideband is never going to give you the best performance.
Thank you. I just raised it because yesterday they said that the ngEHT is going the other way. They're going to double sideband.
And I think that that's exactly the difference between having a large part of your key science being continuum versus having a large part of your key science being spectral in nature, as to which choice is the best one to make for a particular facility.
Okay, thank you. One quick question again, maybe from Shep.
Yeah, just to clarify, that ngEHT is preserving single sideband. We're not going to double sideband. We'll still have an upper sideband and a lower sideband. So I had a question for you, Sean. The two things that are most important for us would be subnetting, phasing up, as you said, one group of antennas at one frequency and one group of antennas at another frequency, and then being able to do that at those two different frequencies. I heard, I think separately from Crystal, that those were not on the critical path, that they would not be ready in the first instantiation of this new correlator upgrade. So does that mean they're not funded? And is there an opportunity for this community to raise some funds and get engaged with working on that?
Yeah, so that's exactly what it means. So there's not all those capabilities on that list will be necessarily available out of the box, and it will require additional resources to develop them and bring them to fruition. So that's a good example of where a community like yours on the call here could actually perhaps seek those resources and provide that capability, or at least bring it to fruition within that correlator system.
Okay, so look very much forward to talking with you about that. There's a lot of possibilities there.
Okay, thank you. We have just one more minute for Sridharan, if he has a quick question, and then we break.
Thank you. I just wanted to ask, I'm a little puzzled by the lack of emphasis on improving the surfaces of the antennas. They are 25 micron, and you know very well that these antennas can be set down to much lower levels. I've done that with the Apex antenna, for example, and this will improve the band 9 and 10 operation, and that's normally seen as impacting only one band. But if you improve performance in band 9 and band 10, then that dribbles down all the way down to the lower bands, because you're releasing high quality time for other bands. So why is this not emphasized? I'm just curious.
I think that's not true. I think we put quite a lot of effort into holography. We've now got a permanent holography receiver, transmitter, I should say, on the side of Serahona. But appreciate, this is not a one antenna kind of deal. We have to do this for 66 antennas to bring it to full fruition. And that has to be, the priority of that has to be mixed in with all the other activities that we do. And so I think we put effort into holography and ensuring our telescopes surfaces have the best RMS we can at any given time. But the cycle time for doing that for 66 antennas is pretty long, given all the other challenges that we have, especially with the recovery from being shut down for nearly 8 months in some instances. So I think it's not true to say we don't put effort into it. We just haven't. I didn't highlight it today because it's part of regular operation today.
So if I could just add, TK, one of the things to imagine is that our situation is quite different from Apex in that we pick these antennas up and bring them down for routine maintenance, normally about once every year or two. And every time they come down and go back up, they get severely shaken. And so it's not a matter of setting all of these things perfectly once. It's a matter of going back and having to reset them almost on a yearly basis. And so that's a much bigger complex problem than sort of perfectly setting Apex and then having it last for years.
Okay, thank you. Maybe I'll talk to you both offline. Thanks a lot.
Thank you. I think that we can break here. The next session will be shifted by 5 minutes. So it will start 5 minutes after 4 UT. And I thank you all. Thank the speakers for this very interesting session.